applications. Before we get into our word problems, we need to identify what key features are we going to use in order to do the applications of derivatives in real-world context. So when we are looking at a graph of any kind of a curve, we are going to be talking about key features as it relates to the graph and its derivatives. Particularly, we are interested in special cases of zeros. And so where is the zero on the graph, meaning x-intercepts, or where are the derivatives zero? Those are going to be really key pieces of information. So when we talk about an absolute maximum, another word that is often used for this is a global maximum. We're talking about the absolute top value of a given graph. So in the picture beside us, the absolute top value is this point right here. So this is an absolute maximum. The coordinate for it is 7, 6, and it occurs when x is 7. So when we are looking at maxes and mins, we're looking at the location of them on the x-axis. So an absolute maximum occurs when x is 7, and an absolute minimum occurs at the lowest point of the graph, which occurs here. The coordinate for this one is 2, 1, and the location is at x equals 2. Now, the other way that we can describe maximum and minimums, if we have a graph that goes on and on forever in either direction, we're not always going to have an absolute maximum point. So what we can talk about is a relative maximum, or another word for this is a local max or min. So these are two words that we're going to use often together. Okay, and the local is where is it highest in a certain window. And so here we can see there is another maximum. It's a local maximum, not a global maximum, but it's a peak in the graph. And it occurs at the coordinate. I'm going to change my pen color here. It occurs at the point 4, 5. So the location is where x is 4. We have a local maximum. So it's a max relative to where it is. And in terms of a minimum, there's one here. Ooh, I should use a different color. There's a minimum point here and a minimum point here. So we have two low points here. So two relative minimum locations at 5, 3 and at 9, 2. And the way that we describe this is it is located at x equals 5, located at x equals 9 as well. Yes?
Global maximum and minimum not be
Yeah, absolutely can. If you're not sure where the global is, or if it has a global, then all of the peaks become local max and all of the valleys become local min. And you can certainly include the absolute max and min in that calculation or in that list. However, if you know that there is a global max and a global min, you can either see it or you can calculate it, then they would be separate. Good question. Yes.
Like in positive x and positive y.
Yes.
Does the absolute maximum and minimum mean that it can also be like negative y-axis?
No, it has nothing to do with that. It is, I know, the English language is fun, isn't it? So when we're talking about it, and this is why I prefer to use the word global, because I mean the topmost y value. Where does that occur? In this case, it occurs where x is 7. When I talk about minimum, we're talking about the lowest possible y value on your graph, and in this case, it occurs at x equals. So it doesn't really have anything to do with absolute value function. It's just a way to describe a max and a min. So either it is the topmost, meaning the global max min, or it's a local one, meaning it's a peak or a valley, but not necessarily overall for the entire graph. Okay, so in general, the way that we're going to describe this in function notation is that if the value of a function at x equals c is greater than the function at f of x for all the x's in the domain, then the value of x is c, or the function at c, is an absolute maximum. So if there is a value c, x equals c, where I put it into the function and the value is higher than any other value of x, then it is an absolute value or a global maximum. Similarly, if there is a number c where I put it into the function and all of the other values are greater than that, then we have an absolute minimum or a global minimum in this function. And often you'll see when we start doing applications, it'll ask you for what are the extreme values of the function. And this is a short way of saying find all the maxes and minimum values. Okay, so if it's asking you what are the extreme values of your function, we are looking for first global max and mins. And if you find no global max and mins, then can you identify local max and mins? Okay, so again, we're going to start off with a simple example. Example 1, what are the extreme values of x squared? Let's sketch a picture. This is a quadratic centered at 0, 0, going up. What features, what extreme value features do you see here? Yeah, so it has an absolute min or max. Min at the point 0, 0. Because this is a function that has a domain of x is all reals and y is increasing no matter what x we put in, 0, 0 is our minimum. This has no absolute max. So if it doesn't have a highest peak, then we check for, are there local min or max? This is a question to you. Are there any other peaks or valleys in this graph? No. So this graph has only one extreme value feature. It is an absolute minimum or a global minimum at 0, 0. Yes, sir. They would be both global, yeah. Okay, example 2. What are the extreme values of 1 minus x squared between, this is important here, look at the restrictions. I'm restricted between 0 and 1, 0 inclusive, 1 exclusive. Do we recognize this function? What would it be? It's a transformation of x squared, right? This is saying negative x squared plus 1. And if we remember our transformations, this is upside down or a reflection over the x-axis and then up 1, right? So if I were to graph this, this is up 1. Okay, tell me the coordinates of the x-intercepts. Yes, 1, 0 and negative 1, 0. And what is the equation of the vertex or the coordinates of the vertex? 0, 1. Okay, so this is the function negative x squared plus 1. If I restrict my domain, I'm going to color over it in blue. I am including 0 and I am excluding 1. So I'm only interested in this part of the graph. So now if I focus in on the blue I've written, what are the extreme values of the blue picture, not the pink picture? 0, 1 is a what? It is a global max. Oops, I don't need a bracket there. Anything else? What's 1, 0? It looks like 1, 0 is a global min. Why is it not though? It's a whole. Yes, we can get infinitely close to 0, right? I can put in the value x equals 0.00001, but then I can make it even smaller, 0.00001, and there will be no value of x that I can put in where I can't find a smaller number. So because I can get infinitely smaller, I have no minimum because I can always do a smaller number. Okay, so if you have a point that you can approach but not touch, you cannot count it as part of your graph. Yes?
Why is not a point just after 1, 0, not like global min?
Say that again.
On the graph, like when you trace the path, point just like after 1, 0.
Right here, you mean?
No, like in the direction.
In the negative.
No.
I think she's saying 0.99990, the global min.
Same idea. X equals 0.999. Well, I can make it bigger. I can make it bigger. How many 9s would make it the minimum? Infinite. Right? So for any number that I can get approaching this 1, I can always find a number that's bigger, which means my y value is going to get closer to 0. And whatever number I find, I can always find a smaller number. So because of the way that numbers work and I can get infinitely close to 1, that infinite piece means I cannot there's no limit. Right? I can't go to that number. So I can't say this is the cutoff. There's no minimum. Even though it's very visually deceptive, right? So if you have a hole, you cannot use your hole as a max or a min because your graph approaches it but doesn't reach it. So it cannot be included. Okay, flipping over the page for Matt's theorem. If f, the function, has a local max or min at c, a value, then either the derivative of the function evaluated at c is 0, or doesn't exist. Where have you been, my friend? It's so good to see you. I feel like I haven't seen you in many, many, many days. Okay, so again, repeat this. This will carry us through 90% of this unit. Basically, what it's saying is if you have a function, here's f of x, and at a value of c, x equals c, you have a local max or min, then the derivative at that point must be 0. We already know this from sketching curves in the last unit, right? At a peak or a valley, when the function changes direction, the instantaneous rate of change at that point must be 0. Alternatively, it could just not exist. For example, if we have a absolute value function, Here is a change in direction, right? This is a local minimum, could be a global minimum, doesn't matter, but f prime does not exist in an absolute value function, right? So this is an example of f of x equals absolute value. This is an example of sine x, right? So if you have a peak or a valley, your derivative is 0. And if you have a sharp corner, it doesn't exist. Both of these mean that there must be something going on in those locations. So you're either looking at a max or a min. However, warning, put it in a box, highlight it. Do not think that this will tell you the location of all your extreme values simply by setting the derivative to 0. Okay, if you know it's a local max or min, then the derivative is 0 or doesn't exist. But the opposite doesn't work. If the derivative is 0, it doesn't necessarily mean that you are at a max or min, because you could just have a flat line. A flat line doesn't have a max or min. It has a derivative of 0, so the backwards of this doesn't work. Just like all thumbs, fingers, but not all fingers are thumbs, right? It works one way, but not the other way. Okay? All right, let's do an example here. If we have that the function is x cubed, then let's calculate its derivative. F prime of x is 2x squared. No. What's the derivative? 3x squared. Thank you for that. Okay, if I set my derivative to 0, what must the value of x be? Oh, I wrote that backwards. X must be 0 then, right? If the derivative is 0, so is that true? Is this then a local min-max? What? We know what x cubed looks like. X equals 0 gives me a special case where I have an x-intercept, but it is not a max or min. Okay, so here's another example where the reverse is not true. Finding a derivative of 0 tells you a key feature of the graph, but it does not tell you if it's a max or min. You got to investigate to determine if it is a max or min. And here again, this is a mathematical example. When we have an absolute value, one. Do we remember making this a piecewise function from last unit? Yeah, so when we have an absolute value function, it becomes a piecewise function, so we have to have a piecewise derivative. So what does that derivative say? If x is 0, f prime of x cannot be 0 in this case, which means it does not exist. And if we look at the function, this is f of x. Oops. -1. This is f prime of x. The original function, f of x, has a minimum at 0, 0, but we're not able to tell that just by looking at the derivative. Okay, so how do we identify this? How can we label it in a way that makes sense in terms of applications? Bless you. we are going to be calling them critical numbers or critical points. So a critical point of a function f is a number c in the domain such that we either have a derivative of 0 or it doesn't exist. So this is going to be called a point of interest or a critical point. It's not going to tell us if it's a max or min, but it's going to tell us something's happening here. We need to investigate it. Okay, so now taking that idea, let's go to the next example. Am I going too fast or am I okay? Okay, okay. Let's go to the next example here. Find the critical numbers of the following equations. So let's find the derivative first. This is going to be 3x squared plus 12x plus 9. Critical features occur when the derivative is 0. So we need to factor and essentially find the zeros, right? So I can divide everything here by 3. And hopefully we can agree that x plus 1, x plus 3 is what we end up with. So this is telling us that x equals -1 and -3 are our critical points. To find the location of those points in the graph, all I have to do is find what is f evaluated at -1, what is f evaluated at -3. At those critical points, I'm just going to grab a you know what? Can you just believe me that I did it on my calculator already? Okay, at -1, the value of the function is -2, and at -3, it's +2. So my critical points occur at -1, -2, and -3, +2. So this is telling me I either have a maximum or a minimum, or maybe a change of direction, or maybe there's a whole, something's going on in the graph that we need to take a look at. And for f of x, or which is, I already did this last page. Okay, so the critical point here would be 0, 0. Okay, closed interval method. Highlight this box or put a star next to it. We need to know this. So put it on a flashcard and start memorizing. Okay, so to find the absolute max or min values of a continuous function of f on a closed interval, closed meaning inclusive, a and b, so from a point to another point. Find the values of f, the function, where you have critical numbers exclusive of a and b. And then find the value of f at the endpoints. Okay, so what I'm saying is find where f prime is 0. Oopsie. Try that again. Find where f prime is 0 or doesn't exist. Find f of a, regular, not prime, and f of b, and compare the critical points and the endpoints. The largest values between these points is going to be your max value, and the smallest will be your min value. Okay, so derivative, we can't take derivative of endpoints, right? So we're going to take the derivative of everything in between, find the critical points, and compare them to the endpoints. Max value is your maximum, min value is your minimum. Okay, so let's do this, put this into practice. the absolute maximum and minimum values of the following function. Here is our interval. Okay, first thing I'm going to do number 2 and then number 1 just because it's slightly easier, at least easier to see. What is the function when x is negative 3.5? And what is the function when x is 1? Take a moment, grab a calculator, sort it out. These are our endpoints. So I want, what is the y coordinate when x is negative 3.5? What is the y coordinate when x is 1? You can just shout it out when you got it. Who's got the 3.5? Michael, you look like you're on task. Thank you. Yes, 1.125. Okay, and who's got the 1 value? 7, 18. Thank you. Okay, so here are 2 endpoint coordinates. We got them. Now let's take the derivative and find the critical point coordinates. So if I take this derivative, f prime, 3x squared plus, oh, this is the same as before, 12x 9. This is from example 4. Okay, so f prime evaluated at, we found the critical points were, again, and this is from example 4, -1, -2, and -3, +2. Right? The critical points were inside of our interval. So that checks out. So now what I want to do is I'm going to compare these 4 points. Look at the y values. What is the highest y value? What is the lowest y value? 18 is the highest, so we have an absolute max at the coordinate 118 and an absolute min where? -1, oopsie, -2. Okay, so if you give it a function and give it an interval, take the derivative, what are the critical points? Then look at the endpoints and compare. What's the most, what's the least? Okay, example 6. New function. Again, a cubic. You have a new interval. So again, we want to compare endpoints versus critical points. Critical points is where f prime is 0, and endpoints is just f of -1/2, f of +4, based on the interval they gave us. Yes, sir.
Before the other 2 points, just like random local maximums.
Before what?
And the last question.
Yes.
What were the other 2 points that we didn't get?
The other 2 points would be a change of directions or local max and mins. Yeah, so yeah, this is a method to calculate the absolute max and mins or the global max and mins inside of an interval. So every other critical point is either a local max min or it's a change of direction point, but it's not the global. Yeah. Gentlemen, you're not doing calculus, turn around and get to work. Are you sure?
Yep. 0, 0, and 3 and 1. Which I was discussing at
So on your screen, you should have I didn't do all the work in between, but you should see the gist of it. I took the derivative, I found the zeros or the critical points. Where is it 0? Right? I take my critical points and my endpoints and I'm putting them into the original function. Here is my maximum value. Here is my minimum value. So I have in this interval an absolute max at the coordinate 4, 17, and an absolute min at the coordinate 2, -3. Questions, comments, concerns? Okay, last 2 examples are slightly more challenging, and we're going to do one word problem in that as well, okay? So same idea. I want you to take a head start here. I want you to find the absolute max and min in the function given, slightly more complex function, so you're going to use your derivative rules. Look at the endpoints, look at the critical points, tell me what the absolute max and min are. So I'm going to give you a head start. And then I will write out the full solution. So take a moment.
Yeah, that's why I didn't turn it on yellow. Did you go press the base to the conversion?
Yeah, go ahead. Gentlemen, you are not using appropriate language and you are not using this time wisely. Turn around. Okay, so on the screen, these are the endpoints. And these are the critical points. I'm just going to call them CPs. Okay. Looking at the question, the first time around when you do this question, as you're looking for the derivative to be 0, this is very easy to miss. When looking at the derivative, if you have an x in the denominator, you have an opportunity for the derivative to be undefined where x is 0. If you have the x in the denominator, right? Or wherever the denominator is 0. So even though it factors out, and you can collect like terms and get to the fact that when the derivative is 0, we have a value of x equals -2, you cannot forget that this is still a possibility. Yes, we factored it out, but if that denominator is 0, we have an undefined, which fits Fermat's theorem, because it says, where is it 0, where is it undefined? Two conditions. Yes, sir.
I know you wrote plus x, like the cube root of x, right? Then it would be the cube root of x squared.
Oh, yes, sorry. Thank you, thank you. I miss it in other places too. When I factored it out. Yeah, okay, sorry, thank you. No, this should not be it. There, okay, fixed it, thank you. Okay, any questions from this question before I scroll into the word problem? Going once, going twice. Okay, let's go. Question 8, this is our last one. This is our word problem here. So the Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model of the velocity of the shuttle during this mission from liftoff at t equals 0 until the solid rocket boosters were jettisoned is at t 126 seconds is given by the following really ugly function. Gentlemen, I'm not going to talk over you, and this is your last warning. Thank you. So they've given us a function of velocity, and what we are looking at is the interval inclusive of 0 and 126. So although this is ugly, this is not, I don't know, new, right? This is still a cubic equation. We know how to do derivatives. This is now very much a calculator question. So be very careful when you're typing these numbers in. Okay, so it says estimate the absolute max and min values of the acceleration of the shuttle between liftoff and jettisoning the boosters. So what we are looking for is the interval, but we're not going to be using the velocity. We're going to be using the acceleration. So very carefully, we need to find essentially the derivative, right? So this is going to be 3 times big ugly number t squared minus, oh, I'm going to run out of space. Hold on, I need to move this over. There we go. Minus 2 times big ugly number plus 23.61. So looking at the acceleration, we want to know what is the acceleration evaluated at our endpoints. A of 0 is the same as v prime of 0, and then a of 126 is the same as v prime of 126. So we're going to take the equation we just found, plug in 0, plug in 126, and we should get coordinates that represent the following values. Where did I say A is 023.61? You're welcome. And for 126, the acceleration was 62.87. So we're not looking at the critical points of the velocity, we're looking at the critical points of the acceleration. So what I need to do now is do the derivative again. Right? Now I want to know what is A prime. In other words, what is V double prime? Anybody know what A prime is called in physics? Jerk, yeah. 0.01302 t minus 2 times 0.09029, and that's it. Right? So critical point occurs when A prime is 0. So what I want to do is take this equation and make it 0. What kind of equation do we have here? Linear, cubic, quartic. Linear. Oops. That should have been a 9 there. 9029. So when we found the acceleration, we ended up with a quadratic. So we can either have 1, 2, or none zeros. When we have a linear equation, how many zeros are we looking for? Just 1, right? And this is bed mass, right? This is the same as saying 0 equals 3x minus 2. We can do this. The numbers are uglier, much uglier, but essentially this is what we're looking for. So we're going to add 2 times blah, blah, blah to the other side, and then we're going to divide by 6 times blah, 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 and then that's going to give us our prime value. Okay, so A prime equals 0 when t equals, you tell me, round it off to 2 decimals. Say again? It's 0? No, the final answer. Round the final answer to 2 decimals. 23 point, yes, that works. 23.12. Okay, so these are our endpoints and endpoints. And this is my critical point. So the final thing I need to do is what is the acceleration at my critical point, 23.12. So you're going to take this number and put it into the acceleration equation that we found here. Tell me what value you get. Bless you. Bless you. What are you guys getting? I like how 3 of you have a calculator and you're still looking at me. You have an equation. I told you the point. Just chuck it in. Tell me what you get. 21.52. Okay, so my critical point happens at 23.12, comma 21.52. So now I'm comparing the extremes. What can you tell me about it? Max is at 126, comma 62.87, and min is at what? 23. So the min is essentially the critical point is our minimum. 21.52. Okay, so ugly question in terms of the numbers, but we're following the same method. We have an open interval, or sorry, a closed interval, check the endpoints, find critical values, compare the y's, and off we go. For your homework, I am going to say that from this point on, consider this extra practice, but hint, hint, nudge, nudge, it will come back. I would focus on these for today. All right, so we are done for today. Rest of class, you've got about 15 minutes. If you could please try a couple of these questions.